Okay, now it should be working.
And I can minimize it here. Or... Okay.
So I think everything's working. Except maybe if we turn off the front light or something. Okay. Yeah, I mean, Maria already, she introduced us to number theory, indeed.
Hi. So I will tell you at the end of the talk about many of the things that we have in number theory, both in Mathlib and in other Lean projects that are built over the library. But for today's tutorial, I want to focus on something more specific. So I'm going to talk about the Gaussian integers and how we can construct them in Lean and prove things about them. So the first part of the talk is going to be adapted from Mathematics in Lean, section 6.3 of that book. And then the next part is about units and prime elements in the Gaussian integers. That part is not in the book, but hopefully you can follow from what I wrote here and the exercises. Okay, so let's start with the definition. So by now, we have already seen several different ways of formalizing a definition in Lean, right? So the Gaussian integers, well, the mathematical definition is that they are defined as the set of complex numbers of the form a plus bi, where a and b are both integers. And this gives us several ways of putting this into Lean. So the first way is the way that I'm following here, the way that is defined in the book. Just define a structure, right? So we can define a structure Gauss int with two fields, one field for the real part and one field for the imaginary part. Of course, if we do this, we are only defining this as a type, right? So we will have to then tell Lean how to define the addition and multiplication and so on, and we'll have to prove that this is a ring. There are other alternatives, right? Instead of like doing this structure kind of definition from the beginning, we could define it as a subtype of the complex numbers or even as a subring of the complex numbers. And of course, for that, we will have to prove that addition, for example, that the addition of two Gaussian integers is still Gaussian integers and so on. So yeah, there are several approaches. We are going to stick with this one. We put this X here so that we can easily get dilemmas about how to check whether two Gaussian integers are equal. So, for example, I get for free a lemma that tells me that two Gaussian integers X and Y are going to be equal when the real parts are equal. So this is this first condition here. And then also the imaginary parts are equal. And then we also get an if and only if version of this lemma. And also we can use the extensionality tactic, ext, because annotation. Okay. Now, so far this is only defined as a type. So let's see how to make it a commutative ring. So for that, I need to tell it what addition is going to be and what multiplication is going to be. And both of these operations are the operations coming from the complex addition and multiplication. Right? So for example, if I want to add a plus bi and c plus di, what I have to do is I have to add the real parts, and that's going to be the real part of the sum, and then the imaginary part of the sum is the sum of the imaginary parts. So that's this first line here. So here we are declaring this as the addition instance. So we are saying that on this type of Gaussian integers that we just defined, we have a way of adding elements, and that way is given by this formula. And then we mark it as an instance so that Lean is going to recognize it immediately, and it's going to allow us to use the usual add notation for it, the sum symbol. And then we do the same with the rest of the operations and elements, right? So negation is defined also in the way that you would expect. The zero element is real part 0 and imaginary part 0. And then multiplication, again, is just the one coming from the complex numbers, which means that it's given by this formula. So the real part is AD minus BC. The complex part, the imaginary part is AD plus BC. Okay. Now, whenever you write a definition like this in Lean, there's a bunch of like very basic lemmas that are mathematically trivial, but you want to add them so that Lean can work with these things more easily and can simplify things for you. So that's what's going on in the next few lines. So for example, zero def, this is just telling me that the zero in the Gaussian integers is just this element 0, 0 that we just defined. For example, addition def, this is telling me that x plus y is the same as adding real parts and imaginary parts. And all of these lemmas, in all of these lemmas, the proof is REFL, meaning that all of these are true by definition, but it's useful to have them sometimes so that we can rewrite. Also, it's useful to have the same lemmas, but for the real part and imaginary part. So these are these lemmas here. For example, I don't know, mul real, this is telling me what the real part of a product is. And then all of these lemmas are marked with this sim tag. So this means that we are going to add them to the list of lemmas that Lean uses to simplify expressions. So we'll see some examples later when we are going to use simp and Lean is going to use some of these lemmas to make our lives easier, I guess. Okay, so we haven't really done anything interesting yet, but with all of this, we can now prove that the Gaussian integers are a commutative ring. So for that, we want to put a commutative ring instance. We will first put all of the data fields. So 0 is equal to the element 0, addition is the addition that we just defined, and so on. And now we have to prove some axioms that they satisfy, right? So I will do one here, and then, well, if you look at these proofs, you can see that all of them look essentially the same, but let's take a closer look at one of them. And then hopefully from that, you can understand what's going on with all of them. So, okay, here I want to prove that addition is commutative, right? So for every pair of Gaussian integers, a plus b is b plus a. So I'll start by introducing the two variables. So I'll do intro AB. Sorry. And now,
Can I ask something?
Yeah.
When you offer a Gaussian, you already get explanations. Where did this come from?
Oh, this comes from the comment that I wrote on the definition. So if you mark the comment with, instead of just one dash here, you put two dashes, this is going to be interpreted as the doc string for the definition. So yeah, so when you hover over this, you will see this comment that I wrote. Also, in the HTML version of the documentation, you will also get this information. Okay, so where were we? Okay, yes, so we want to prove a plus b is equal to b plus a. Remember, if we want to prove that two Gaussian integers are equal, we have to check equality for real and imaginary parts, and we can do that. We can separate into that using the X tactic. And now we have two goals. We have the real goal and the imaginary goal, right? So focus on the first one. So here I just have to do the real part of a plus b is the sum of the is the real part of b plus a. To do this, I'm going to try simp. And yeah, so you can see that this did simp only at real. So this is one of these lemmas that we have marked with the simp tag at the beginning. And now, well, now we can, we could just apply the lemma that tells me that addition is commutative. So I could do rewrite at com. And this now works because the integers are a commutative ring. And if maybe this expression that I have is a bit more complicated, or I don't want to think about what the exact lemma, the exact name of the lemma is going to be, instead I can use ring. And similarly, if I don't want to write this explicitly, I can just do simp. Okay. So now I have to do the same for the imaginary part. So I can do, if I try to do simp only, it will tell me that now the lemma that I'm using is add im, and then I can again use ring to close the goal. So essentially, this is what's going on in each of these. So yeah, let's see how to compress all of this. So first, I'm doing intro AB. So I can also do that with intros, and then Lin is going to introduce as many variables as it needs. Then the next instruction is ext. But actually, we see that in this case, both of the proofs, both of the goals can be proved exactly with the same tactics, right? So what I can do is I can use this tactic combinator so that tactics get applied everywhere. So now I can delete the second part. And then similarly, I can combine here again. And that's how this becomes just one line. Okay. So yeah, if you were wondering how we got to this, well, probably we first wrote a longer version at the beginning and then we simplified. Okay. Yeah, the next thing is some lemmas that are going to be useful to regard natural numbers and integers as Gaussian integers. So for example, here we have a lemma int cast. This tells me that if I cast x to the Gaussian integers, this is going to be the Gaussian integer whose real part is x and imaginary part is 0. So then, again, I want to have some simple lemmas for the real part and the imaginary part so that the simplifier can work for us. And then similarly for natural numbers, we have the same kind of lemmas. Okay. And then some easy things that we prove is we prove that the Gaussian integers are non-empty, so they have. Yeah. Yes.
So what would be the goal here? What
Here? Yeah, so the goal tells you, so since we have proven that the Gaussian integers are a ring, that means that there is a way to include the integers, right? So there is a coercion map. So that's what we have on the left-hand side. And then on the right-hand side, we have the Gaussian integer constructed by feeding it real part is equal to x and imaginary part is equal to 0.
Saying we do have the cast already, and this lemma is saying that this is actually
yes,
this one.
Yes, exactly.
Where did the cast come from? You said because you made the ring.
Yeah, so whenever you have a ring, part of the data is how to cast a natural number and how to cast an integer. That's where the coercion is coming from. Okay. Okay. So now we can check that this is non-empty. For example, 0 is an element. And we can also check that it is non-trivial because 0 and 1 are two different elements. Okay. Now let's do something a bit more interesting. We are going to prove that the Gaussian integers are an Euclidean domain. Loosely speaking, what this means is that they have a division algorithm that behaves like the division algorithm in the integers. And being a bit more precise, these are the, oops, sorry. This is exactly what we will have to check. So we have to check that they come equipped with some norm function. So some function from the ring to the natural numbers that satisfies two properties. So the first property is whenever I have an element A and a non-zero element B in my ring, I can find a quotient and a remainder such that A is equal to BQ plus R. And the condition on the remainder is that either the remainder is equal to 0 or the norm of the remainder should be less than the norm of B. So that's the first condition. The second condition is that for every element A and every non-zero element B, the norm of A has to be less than or equal to the norm of the product A times B. Okay, so if we want to prove that the Gaussian integers satisfy this, the first thing to do is define the norm function. So in this case, the norm of a Gaussian integer is defined as the square of the real part plus the square of the imaginary part. And then there are some properties that are useful to have for this norm. So these are to prove, so maybe I'll do a couple of them here, and then the rest are exercises for you. So for example, I want to prove that the norm is non-negative. Hopefully I can use the positivity tactic here, but if I just try to use it directly, this is probably not going to work because Lin doesn't really know what the norm is. So it tries to apply the tactic, but it doesn't know what the norm is, so it cannot make progress. However, what I can do is I can first simplify the definition of the norm. So I can do maybe rewrite norm or simp norm, so that this becomes the square of the real part plus the square of the imaginary part. And now positivity works. Okay, so this was almost immediate. Yeah, the next few theorems are just essentially telling you that 0 is the only element with norm equal to 0. For this, helpful lemma, which of course is mathematically trivial, is x squared plus y squared is equal to 0 if and only if x is equal to 0, y is equal to 0. So this is something that you should be able to prove. And then you can use it for these three lemmas here, I guess. And then, for example, if I want to prove that the norm is multiplicative, again, I can start by rewriting the norm. And then if I don't want to do this 3 times, maybe I'll do simp only norm first. And then I can again try simp to see if it makes any more progress. It will, because it knows how the real part and the imaginary part of the product look. So it will use these lemmas. And then hopefully Rin will finish for us. Okay. Yeah, this you can probably skip, but this is just telling you that since the norm is always going to be non-negative, you can also view it as a natural number and some coercion lemmas for that. Okay, so maybe let's skip those 3 lemmas, and then a couple more things. The norm of an integer is equal to the square of the integer, and same for a natural number. Okay. Yeah, and the last thing that I asked you to prove about the norm is these lemmas about how it's related to the conjugate of an element, right? So the conjugate of a Gaussian integer is same real part and then the negative of the imaginary part, and then the norm of an element is going to be the element times the conjugate. Okay. Now, for defining this Euclidean algorithm, we first need to know what the, we already know what the norm function is, but we also need to know what the division is going to be, right? So for that, let me skip this for now. These are some auxiliary functions, but the idea is the following. So whenever we have 2 Gaussian integers, we can divide them as complex numbers, right? So if I want to do x over y, what I can do is I can multiply both the numerator and the denominator by the conjugate of the denominator, and then this is the formula that I get. The problem, of course, is that in general this is not going to be in the Gaussian integers anymore, right? Like the real part and the imaginary part in general will not be integers. However, what we will do is we will approximate to the nearest Gaussian integer, and that's what we are going to take as the quotient. Okay, so x divided by y in the Gaussian integers is going to be the closest Gaussian integer for that. And I won't explain exactly how to get the formulas for that because it is just a computation. If you want to look more closely into this, you can read the Mathematician book where it explains exactly how they came up with these formulas. But These are just the formulas to get the closest Gaussian integers to the complex division. Okay, now we know what the quotient is going to be. We also need to know what the remainder is going to be. So the remainder is going to be x minus this quotient multiplied times y. Okay, so now we need to check that with these definitions of quotient and remainder, the properties of being an Euclidean domain are satisfied, right? So the first property is, well, first I want to prove, that the norm of the remainder is always less than the norm of y, assuming that y is not equal to 0. And then, so this one, I already gave you the proof here. And then property 2, this one I left as an exercise, is proving that whenever you have an element x and a non-zero Gaussian integer y, then the norm of x is less than or equal to the norm of the product. Okay, now once we have all of this, we can get the Euclidean domain instance.
I saw that you could do inequalities in these calc blocks.
Yes. Yes, you can.
In general, what kind of relations can you fill in there? And I'm wondering, I thought it was only possible for.
No, it's possible. It's also possible for inequalities. So equalities and inequalities.
Like divisibility or something.
So good question. So this says a stepwise reasoning over transitive relations. So maybe, yeah. I think I've only seen this with like equalities and inequalities, but maybe you can use it more generally. Yeah, I don't know. Okay. Okay, so now assuming that we have proven these lemmas, we can put everything together to get the Euclidean domain instance. So so we already proved at the beginning that they are a commutative ring. So we are going to take that. And then we have to add what the quotient and the remainder are going to be, like how they are defined. And these are these two things that we just define here. So this deep instance and mode instance, these are the quotient and the remainder. And then, we have to prove the properties. So the interesting properties here are first this one. So for every pair of Gaussian integers, b times a over b plus the remainder is equal to a. Right, so this is the first thing that we want to be true. And then the other interesting one, I think, is this one. So so this is the one telling you that the norm of A is going to be less than or equal to the norm of A times B. It looks a bit weird, but that's what's going on. Okay, so then we can already see the type inference system at work here, because we've proven that this is an Euclidean domain, and then mathematically we know that this implies a series of things, right? So, for example, every Euclidean domain is a principal ideal ring, unique factorization domain, and a domain. So these are things that we don't need to write explicitly. So this code isn't really doing anything. This is just to show up that Lean can find these things automatically. So the proof of this is infer instance, meaning that I'm not doing anything. Lean is finding this from the fact that we have proven the Euclidean domain instance. Okay.
But you defined Euclidean domains yourself, or was this something we defined?
So the Euclidean domain is something that's defined in Mathlib, right? And here I'm proving that this is an instance of an Euclidean domain. And then because I proved this, Lean can infer all of the other instances. But yeah, this is in the, well, apparently it's in the file algebra Euclidean domain.deps. Okay. another conclusion that we can obtain from this is that elements, so for elements in the Gaussian integers, being irreducible is equivalent to being prime. So remember, irreducible means if I factor it into a product, then one of the elements in the product has to be a unit. And then prime means that if it divides a product, it has to divide one of the terms in the product. So not equivalent for all rings, but they are equivalent in this case. Okay, now the next part is I want to say something about what the units are in the Gaussian integers and what the prime elements are. So for the units, this is the easier part. The units are going to be the elements that have norm equal to 1. So that's the first lemma that I asked you to prove here. And then we see that there's actually only 4 of them. So the units are going to be plus or minus 1 or plus or minus I. I gave you part of the proof here, and I only asked you to fill in some part of it. I'm sorry here, but yeah, I mean, this is assuming that we know that this sum is equal to 1. We want to conclude that one of these 4 cases has to be true. Okay, now for the most interesting part is what primes are in the Gaussian integers. So yeah, the thing is that if we consider the primes in the integers, some of them are still going to be prime when considered as an element of the Gaussian integers, but some of them we are going to be able to factor, right? So in this part of the file, we are going to try to understand in which cases we can factor. 2 is a very special case. It's very unique for the Gaussian integers because it ramifies, which means that it factors in this specific way in which we have a unique irreducible factor appearing, right? So we can express 2 as minus I, which remember is a unit. So in some sense, it doesn't really count in the factorization, and then times the square of 1 plus I. So yeah, the first thing I asked you is just to check that this computation is true. And then I just need to check that this element 1 plus I is actually an irreducible element. And again, I'm giving you a sketch of the proof, and you only have to check a couple of things here. Okay, so 2 is special. It's going to be the only prime that ramifies in the Gaussian integers. And then we will see what happens with the odd primes. So what we want to prove is that a prime P, and when I say prime, I mean a prime in the integers, is going to still be a prime in the Gaussian integers if and only if it is congruent to 3 modulo 4. Okay, so why is this interesting? Well, it's also related to whether the prime is can be written as a sum of squares or not, right? So the first lemma that we will prove is that if P is not prime in the Gaussian integers, then we can write it as a squared plus b squared for some integers a and b. Okay, so yeah, so this is a sketch of this proof. So first we prove that P is not a unit. Then we prove that we can express it as the product of 2 Gaussian integers for which none of them are units. And then from that, if you think about how multiplication is connected with the norm and so on, you will be able to get to this expression about P is equal to a squared plus b squared. Okay. Maybe the notation is a bit unfortunate because yeah, this a and b is not the same as this a and b, but just be careful with that, I guess. Okay. So we prove that if P is not irreducible, then P is equal to a squared plus b squared. And then here we want to prove some kind of converse. So if P is equal to 3 mod 4, we want to prove that this is a prime element in the Gaussian integers. And then
So what is that aside command?
where, sorry? Oh, here. Yeah. Yes. So the side what's doing here is there's only finitely many cases to consider. So it's like running through the cases, and so that you don't have to do it by hand. That's what's going on. But yeah, so this is when you have a decidable instance, you can try to use this tactic. So in particular, when you are working with the kind of situation where there's only finitely many things to check, sometimes this can do the work for you, or at least make some progress. But yeah, that's what's going on here. So this is only checking some finitely many cases, so you can do it with the site.
But we're saying that finite case is exactly, you have to give a number, let's say 10, and it has to check inside this, let's say 1 to 10, right? Not
Yeah.
for a finite number n, so that.
Right. So in these cases, well, A and B are in C mod 4. So C mod 4 is a finite type, right? It's a type with 4 elements. So it's like, that's why we can use this tactic in this case. Yes, for each of A and B, we have 4 possibilities, and this is running through all of the possibilities. Okay. Okay, so we have proven in this lemma that if P is 3 mod 4, then P is prime. The next lemma is the opposite. So if P is prime as a Gaussian integer, then P is 3 mod 4. Then this is the hardest direction. So I wrote a very detailed skeleton of the proof. In case this is not a proof that you have seen before, or maybe you saw it a very long time ago and you don't remember, which is perfectly fine. But yeah, this is one way to prove this, and I'm just asking you to fill in like some of the computations that you have to do along the way. Okay, and then the last part here is we put both directions together to get an if and only if statement, right? So P is prime as a Gaussian integer if and only if P is 3 mod 4. And from this, we can get the conclusion about whether we can express P as a sum of integers. So at this point, this is almost equivalent to saying that, I mean, almost immediately equivalent to saying that P can be written as A squared plus B squared for some integers C and B, if and only if P is congruent to 1 mod 4. Which is already an interesting result. So this maybe will be one of the highlights of an elementary number theory course or something like that. Okay. Yes, I think this is all I wanted to say about the Gaussian integers, but I also want to tell you a bit more about other kinds of number theory that we have in Mathlib, just so that you have an idea of what's already there. So yeah, I wrote a short list here of things we have. So for example, if you want to do some more modular arithmetic, like we did a little bit here, but not too much, there's this data CMod folder where you can find information for that. We have the p-adic numbers and also the p-adic integers, and we have quite a lot of results about them. Like we have the norm, we have the additive evaluation, we have a version of Hensel lemma for the p-adic integers. This was also one of the first big mathematical objects that were added to the Mathlib library. This is from, I think, from 2018, this formalization. We have a proof of quadratic reciprocity in Mathlib. We have quite a developed theory of Dedekind domains. So we have the fact that you can factorize ideas uniquely in Dedekind domains. And we can also construct the adic valuation relative to a maximal place in a Dedekind domain, a maximal ideal, sorry. And we can even construct the ring of finite totals for a Dedekind domain. We have global fields in Mathlib, not local fields yet, but they are coming very soon. So for global fields, we can even do things like define the class numbers and in some cases compute class numbers. And we will very soon have in Mathlib the definition of the adels and idels for a global field. We have elliptic curves, and this was this was very interesting recently because until maybe 6 months ago or something like that, we had a definition of elliptic curve, but we didn't have a proof of associativity, right? Because well, if you want to do the proof like from the equations, the polynomials that appear are like too big, and Lin could not handle these polynomials. But this year, two PhD students were able to find probably a new proof that they were able to, a new elementary proof of associativity that they were able to formalize in Lin. So this was an example of a case where trying to formalize something gives you some new mathematical insight of how to work with this object. What else? So we have cyclotomic extensions. We have the ring of with vectors. Yeah.
You told us that you tried this himself also,
Yeah.
sensitivity of the group law. The failed was unfolded just too big.
Right. So yeah, exactly. If you try it with the general Weierstrass equation, assuming that you can have characteristic 2 or 3 or something, yeah, the polynomials that appear are too big. So Lin cannot process these polynomials. So yeah, they had to find an alternative proof so that the computations were small enough that Lin could handle them. Yeah. Okay, what else? We have some things about L series, not too much, but there are some things there. Bernoulli polynomials. We have a proof of Liouville's theorem. We have group homology, and yeah, so these are things that are in Mathlib. Let me also show you some projects that are maybe not in Mathlib, but already formalized in Lin. So some of this is like common to the previous slide, but so yeah. A couple of things that are here, but not in Mathlib yet, are, for example, perpetuity spaces. So these were formalized in 2019 probably, and the paper came out in 2020. And they are not part of the library, but this was still a very helpful project for Mathlib because a lot of the background that they had developed for this project, it's now in the library. Like, for example, there's a lot of stuff about valuations that is very useful for other things, and this is in Mathlib thanks to the perpetuity spaces project, right? Bit vectors I already mentioned. There's a formalization of modular forms, but I think it's not in Mathlib yet. I think it's on a separate project. Amelia Livingston, who formalized group homology, is also working on Galois homology now. Ashley Narayanan did Iwasawa theory, also not in Mathlib yet, but it's on a separate project. I formalized the definition of the p-adic complex numbers. Now this is in Lin 3, but I'm planning to port this to Lin 4 hopefully next month and port it to p-adic to the library. There's an ongoing project to formalize Fermat's last theorem in the case of regular primes. And yeah, these are two of my ongoing projects. So with Filippo Nuccio, I'm working on formalizing a proof of local class field theory. So this is a longer term project. So far we have defined local fields and we have developed some of the theory of local fields and fields with a discrete valuation. And then with Antoine Chamberlain, I'm working on formalizing divided powers and the divided power envelope so that we can define the ring decrease. So yeah, this is just so that you get an idea of where the state of the art is at the moment in Lin. Yeah, I think this is everything I had to say. Thanks.
Questions? For local class field theory, do you want to use group homology or anything else?
Do you mean for global class field theory or? So for local class field theory, we want to formalize the cohomological proof of it, because yeah, I think Galois cohomology is not there yet, but it's close, I think. So hopefully we can use that. So we are planning on developing Tate cohomology and go from there, I guess. Yeah, we also considering the approach using like Lubin-Tate towers. But this was before we got more group cohomology in Lean, and now we think that the cohomological approach should be possible. So we are going to try to do it that way. Yeah.
I was also wondering about that proof that is producing two big Lean terms for Lean to process them. How does the paper proof look like then?
You mean for the elliptic curve associativity? Yeah, so the thing is, in paper, like in a textbook, you probably see that proof for the sort by stars equation. Right? So if you are working in characteristic higher than 3, you can use a simpler equation for an elliptic curve, and then the computations are easier because you have less terms in your polynomials. Right? The problem is that if you want to do the completely general case where you allow characteristic 2 or 3, you have to use the general equation, and that's why you end up getting very complicated polynomials. Yeah. So in paper, you probably only see the version with the sort by stars equation, where it's still a long computation, but it's more manageable.
I guess the question is, did any human check before that it also works in characteristic 2 and 3?
I mean, but there are also like some geometrical proofs where you avoid this issue, right? The problem is that in Lean, we didn't have enough geometry to formalize the geometrical proof. Yeah.
And you just have the line as a third point, and it doesn't maybe not so given equation.
Yeah, I don't think that writing the proof using the polynomial formulas, I don't think that's possible by hand in the general case. It's like too big.
Okay, but for the revision tool,
Yeah.
yeah, thanks.
Okay.